Hello and welcome to my CST schematic tool overview about Microstrip transmission lines. So open up a CST schematic tool environment and let's get started. So CST environment, navigate over to schematic tool and let's go into block selection tree and check out what we can do with Microstrip. So in the previous video, we looked at ideal transmission lines and we did an optimization sweep to actually get a wideband performance over a set frequency. Let's try and recreate a similar environment, but in Microstrip. And it takes a little bit more extra effort. So to do wideband impedance matching, either go to the textbook, figure out what those impedances are, and then you can use something like the analytical line impedance tool. You go thin microstrip and you can calculate the impedances and so forth, calculate the line lengths of a phase shift of 90 and so forth. But if you don't have any of that information, we can also use the optimizer or tuning or parameter sweep. So schematic tool, here we are. Now I want to do a third order system and I want it centered around 5 gigahertz, let's say today. So I'm going to create another network and I am doing a impedance match to, let's say, 250 ohms again. Okay, so let's grab out a circuit element and do a resistive load and then set it to be R equaling, so R enter and then 250. There we go, done. I'm going to connect my microstrip block, put a ground to the resistor, and then put a port. And this is going to be my first initial setup. I'm going to just create a task, S parameters, OK. Remember, if this screen doesn't pop up, click over to S parameters and navigate to one of the two boxes down below. And you should have some entering fields where you can say F min, number of points, and so forth. So up to 10 gigahertz, increase the number of points to maybe 10,000 for clearer or better accuracy. But remember, if we're optimizing, keeping those points as low as possible is going to increase the computation, the computation time. So I'm going to work on, let's say, epsilon 4.3. Sure. Let's click on the arrow block to set up our environment. I'm going to use 4.3, and let's say I'm using a height of 1 millimeter. That's perfectly fine. So now I'm going to set the length to be quarter wavelength underscore microstrip. And then I'm going to set it to be a random value of 5. And then I'm going to first set up the width of our random value. Let's call it quarter wavelength microstrip width. And then let's set it to be, needs to be something small if R is going to be around 250. It might not be too possible. Maybe we'll match to an easier value of, let's say, 150. So I'm going to set that to be 0.2. Let's change our R value to something more manageable, because remember, this is 3D parameters, so we're dealing with widths and lengths and millimeters and so forth. So 150, still going to be a mismatch load. Let's click update. Oopsie, needed to change this. Constant, remember, always need it to be constant 50. And let's click update one more time. Okay, we can see at 5, we are getting a match frequency around 8 to 9. I need it to be 5. So I'm going to deselect auto, put a minimum range of 0, a maximum range of, let's say, -30. And I'm going to then go tune, and we're just going to figure out the length of a 5 gigahertz impedance matching network. So I'm just going to play with both values of width and length. So I'm going to play with the width first to just get a match condition, which I've nailed here. So I've just achieved a match condition to change it from 0.2, it was my guess, but I changed it back to 0.7-ish. And you can see I've got a match condition. I'm going to click auto now because I'm happy with it. And now I'm just going to tune the length to bring the frequency down to 5. And I've nearly got it. I'm going to fine tune it a little bit by clicking 8 as a minimum value, and then the maximum value I'm going to set as 9. And now I can slightly fine tune it. And I think I've nailed it pretty much there. So what I've calculated is this line, or this width actually, is going to be the impedance of it is the square root of 50 times 150. So there's one very important thing that I just did here is, let's say in a hypothetical sense, I didn't know what the load impedance was of, let's say, an antenna, or I didn't know what the input impedance is to a certain block. What I've then done is I've calculated, or I've tuned a match condition. Now, if I can then calculate what that impedance was, because I just created 0.7, so I could reverse engineer what the impedance is of this line here. I know I started with 50. If I know I had a line of, let's say, 50 here, and then, I don't know, I got something like an impedance of 100, I could then calculate what the input impedance is of this block here, or if I had an unknown network. So that's another powerful tool. Okay, so I've got the match condition. I've got it at 0.68, and I'm pretty happy with that. And the goal of this was just to tune the quarter wavelength MS here. So now I know the quarter wavelength at 5 gigahertz. Remember, I wanted a wideband system. I can then put the length of these blocks to be all the same. So I'm going to go over to the width, and it's unknown. I'm going to call it width underscore 1, and then I'll set it to be 2. Sure. Close the tuner. This is going to be width 2, and set it as 2, and set them all the same to start off with, and then width underscore 3, sorry, and then make it 2 again. A little confusing, but width 1, width 2, width 3, and now I'm going to set the length of every single one of these blocks the same, which is quarter wavelength MS. Enter. Quarter wavelength MS. So I'm just clicking tab when it comes up to autofill. Length, click Q, tab, click off the screen. Okay, so we've got all the blocks ready. I'm going to copy and paste the load, and I'm also going to attach a port to one of the faces. And I am going to leave this port here as block dependent, just so we can actually find out what the impedance is of one. So I need to figure out what is actually the input impedance here. And we could also find the impedance of this block if I just set this block to block dependent, and it will calculate that. And we'll see it here. So I've set port 2, block dependent MS line. I'm going to click update. Okay. And I'm going to go to port impedance now. And we can see that actually a width of 2, right, has given us a very close attempt at 50 ohms. But I'm just going to slightly tune that a little more. So let's go over to tune, and I'm going to decrease the width and see what happens. Okay, I'm nearly there, and nearly overshot a little bit. Oopsie. Yeah, I mean, that's close enough. Yeah, I'm happy with that. So at 5 gigahertz, we get approximately 50 ohms. And the width of that line needs to be 1.9523. Let's take off some of these values. Okay, so I'm very happy with that. So now we've actually just used the special property of block dependent to actually just fine tune the impedance of a microstrip block. Now that I've done that, I'm going to change off and go to constant because I want it to be a 50 ohm port. And then here are my 3 networks. So I could manually tune this again, but that's going to be pretty painful. So I know, because this is a 150 ohm system, this R value, I know that all of these values here are going to be less than 2. So I'm going to set all of my values here. Let's close the tuner. All to 50 ohms. So they've all been set to 50 ohms. And now I can run my optimizer again. I'm going to use evolution strategy because evolution strategy is very good at guessing values. where trust region is good at fine tuning. I'm going to say you have control over all these values. And I'm going to say, well, actually, you can supply a value between 0.1 and 1.952. And I'm going to change this for all of them. I'm just clicking tab, 0.1, 1.952. So previously I said, well, guess a value between maybe 50 ohms and 250 ohms when we're doing the ideal transmission line system. But rather, we don't have an easy way of saying just set the impedance to this value. We're dealing with the 3D geometry or the algebraic geometry of this hypothetical 3D microstrip. Okay, so I've said you have a large range to choose between. Now it's about setting our goal. So because I've set the quarter wavelength, I actually am not going to give control to the optimizer of quarter wavelength. I would if I wanted to work at 10 gigahertz, but because I've already fine-tuned it, you know, 4 parameters, it could do it, but with 3 parameters, it's going to do a lot faster and have more confidence over it. So I'm going to say use previous data. I'm going to go goals now, add a new goal, dB magnitude, -30, let's say is the target. Edit, sorry again, and then at a range, and I said it was going to be at 5 was the center, 4 to 6. So now it's changing the impedance of these blocks to try and achieve this match condition. And we'll double check all our properties. We're happy with them. General properties, none. I'm happy with everything. Let's click start. Yep. So you can see it's still very fast. Not as fast as last time. Let's click over to S parameters and we can see at it trying to form an answer. So we should be looking at, I think, S22. So this is over 30 iterations. So it's still trying to have a go. It's got a lot of values to pump through and it's just wildly guessing. And the way evolution strategy likes to work is that all of a sudden, once it starts getting kind of good solutions or good answers, it will then start to then drive completely the correct answers. So you see it's still kind of guessing, still wiggling, and we might enter a state where it gets stuck and we didn't supply a better range. So if we knew what the impedances could be, it would have then a better go at it. So as you can see, it might have been wise to create this system in a ideal transmission line environment first, and then translate those results. Another way to speed up the simulation in case you don't see converging results is to go and change the goal. Previously I said if you make the goal very narrow and then start to widen it up, it might be possible to achieve an answer. So we can start seeing that it's getting there, but the bandwidth might be tricking the system a little too much. If you don't see an answer starting to converge, you kind of have two choices. It's how impatient are you? You can just cancel it and then try a different range. But if you go to the info, it's going to stop at 3000. So you can just let it have a go at it. So what I'm going to do now is I'm going to show you how you stop it. To stop it, you want to go to the bottom right hand corner and click this little X, and then just say, choose the best parameter, sure. And then here are the values. Okay, and we can just from inspection looking at it, the first one was 1.95, so it matched it to 50, where we know it shouldn't have. It needs to be a lower value actually. And then these 2 points, we can kind of see the stepping down nature. And so it's going a high, 50 ohms, and this might be 75 and this might be 100. So it's getting the correct kind of nature of how it should look. Rather than such a wide range, let's just see if it can get at 5 minus 0.1, like we previously did, and 5 plus 0.1. Around this range, -30, that's totally fine, but we can also edit it, make it a little easier for the system at -20. And we know that the first element is going to be somewhat below 50 ohms. So I'm just going to force it to search for stuff below. use the data previous, sure. I already guessed it. I guess I have to leave it the same. Bugger. Unless I manually change it. So that's totally fine. Let's see how it goes now and see if there's a difference. So I'm going to set it up. It's going to first run through all the previous answers because I asked it to by clicking this little dot point. So it looks like it's not doing anything, but it's actually going over the previous 88 to get kind of that information for the machine learning or the optimization algorithm. So then I can click over to S parameters, and then all of a sudden, once it's gone through those previous 88 results, you'll start to see the optimizer trying to figure it all out again. Okay. So I'm going to pause my video now, and then I'll come back and see if it was able to converge. Okay, I see one big oversight through this whole journey is that I am actually focusing on S22. So that is most definitely why we weren't seeing any sort of progress. So, silly me, let's go edit again. Let's change it to S22. That's what we're focusing on. So now when I click start, go back to the results here. Okay, now it's actually trying to figure out possible solutions. So, a little bit of an oversight, but it's good that we've realized that. And then now we can see, oh, it solved it straight away. 21 iterations of the algorithm. And it was able to achieve the following parameters we asked for. -20 between a very narrow bandwidth. So I'm going to say, sure, that narrow bandwidth was a bit too easy for you. Let's make it a gigahertz bandwidth. And I'm going to click start. I'm going to see how it goes with this. If you click on result and then head over to optimize the result curve, you can see the goal whilst it's trying to actually solve it. So we're on algorithm 20, and we can start to see that the best so far, oh, it's nearly there. Oh, perfect. It stopped. 35. And it achieved the goal we're looking for. And then we could be a little crazy and just go edit. Let's see if it can do the previous 4 to 6. Click OK. And let's see if it will try and push -30 throughout this whole band. Which may be a bit too difficult, but we'll see how it goes. I click start. Trying to go down to my parameters so I can see what it's doing through the iterations. And you'll find if one gets stuck, or if you're at this stage of optimization, maybe CMA evolution strategy is not the best approach for this, because it's kind of guessing random values, where something like trust region might be actually better to slightly squeeze out all the potential for the system. So you can see if we stated the goal to be actually -20 over that 2 gigahertz bandwidth, it could achieve that easily. And you can see that it's a little bit lopsided, this kind of nature. You expected this sort of Chevy Chev kind of bump along the S22 to be a bit more even. And that's because at different widths, the wavelength isn't actually the same for a 90 degrees phase shift or a quarter wavelength. So if you wanted that to be perfect, you would ask the optimizer then, once it's found a result, to have control of the individual quarter wavelength values, and then say you can only wiggle it just a tiny bit. And then you would ask it to use trust region method, and then it will slightly fine tune. So we can see we're nearly getting results. Let's head over to the best possible result, and look at that. That was very close, but it's still trying just to push it out, because in this mid-band region, oh, there we go. It's still going, because over here it's still not accepting the goal, but it's still going to push through. 140, 142, and that's our evolution strategy. So once it's latched onto a goal, it's trying its hardest to then push through. So we could stop the simulation. You know, this is very good. We're happy with this, but we'll see if it would find another final solution. We can head back over to S parameters to see how well it's doing. Not too well. So we can click abort calculation for best parameter. Perfect. That's the best parameter we got, and that still is very impressive. So now we've taken, well, we've taken no inspiration from any textbooks. We've done zero calculations, but we've just asked the optimizer to have a go. And you can see the performance difference between a single quarter wavelength impedance matching network and a third order system. So if I then increased it to a sixth order, I could say, optimizer, here, have a go at it again. And it will be hopefully be able to do it. If I ask it to do like a ninth order, well, now it's controlling 9 parameters. It's going to run for a lot longer, and it might not be able to converge too well. So there's a bit of a limitation when it comes to this. A third order network, a sixth order. I've previously done a 12th order through optimization and was able to achieve a good result. So it is possible. However, learning this from the textbook and implementing the textbook's impedances will achieve you definitely a cleaner solution. However, this is very quick and easy way to do wideband impedance matching networks. So we're just exploring, remember, microstrip blocks. Let's go through. So we've also got stub blocks we can play with. You can, if I was just creating a network, I could add a couple of stubs in here if I wanted to. Let's move this down. And I could say, you know what, my matching network, you can have 3 stubs as well. Sure. And you could do the exact same process. You have 6 parameters to play with. Good luck, optimizer. Can you achieve an impedance match? So that's what it's also capable of. Okay, let's check out some of the other blocks. Discontinuities. We can see we've got sort of like a cross junction. We've got microstrip gap. So a physical gap between 2 widths or the end of it. You've got this sort of T junction. But remember, when using microstrip, we should have, in this scenario here, if we were then to create it in 3D, it's not going to provide an accurate result. So if we wanted to be very sure, okay, we can actually copy and paste this perfectly working system. Let's move this down. And what we should do is we should just double check before going into 3D that we've accounted for the width size difference. So let's go over to block selection and add this little tool here, which is the microstrip step. And we're going to plug a step in there, copy and paste, and another step. Now, if we click on this block, we can go through the parameters and see we've got a length, and we're going to keep the length of 0. However, you could have created a third order network just with 2 of these blocks. And you could create the first length to be quarter wavelength, the second length to be quarter wavelength on 2, and then the final one would be the first length quarter wavelength on 2, and the second length would be quarter wavelength, and that would achieve a third order system. However, we just want this block here to account for any type of reflections you see from a thin or even just sort of a step within the microstrip lines. Because this first element here, we've stated it's 1.19, and the second element is 1.13. So there is a difference, so a significant difference. It's nearly half the size of it. So there's going to be some sort of reflections. And by not putting this discontinuity block in, we're not accounting for any of sort of these reflections or loss in performance. So when we transfer it perfectly to the 3D environment, it might not perform as we expect. So to do so, we're going to see where it says 1 and 2. Width 1 is going to be width underscore 1. And then the second width is going to be width underscore 2. And then for the second microstrip step, width 1 is going to be connected to this block, which is width 2. So width 1 is actually going to be W underscore 2. And then the last one's going to be W underscore 3. So that's another significant step. I'm going from 1.1 all the way down to 0.3 millimeters. So now that we've accounted for it, let's go to our tasks. Let's not make a block dependent. Let's make it constant to 50. And we can click update. So once it's updated, we can go to our S parameters. And although it's not significant in this sort of scenario, here's our original result. Now, by just having the microstrip steps between it, we see it starting to even out. However, there are reflections between each single step, and those reflections show a poor performance, although both of these systems perform very well. So rather than optimizing for this system, it's more wise to actually ask the optimizer to optimize for this network here. It doesn't have to control any more. For example, it's still controlling just 3 values. However, you've accounted for the S parameter losses between this microstrip step. Okay, so, and the same goes if you want to use a coupled line, for example here, a coupled line to another coupled line which had a different kind of length to it, or different, sorry, thickness or width, you would then need to add a similar block, or you can add one of these steps to it, and that will account for the shift in width and so forth. And you can create sort of hairpin networks, you can create coupled line filtering networks and so forth. So the last thing I'd like to go over is just couplers down the bottom. If you click on something which is quite common in microstrip design, which is a branchline coupler or branchline hybrid, and the rat race coupler here, or rat race ring coupler, these tools have been formulated for you, but it's a bit hard to distinguish, well, what does transverse spacing and longitudinal width, what does that actually mean? So the easiest way when you're trying to figure out what any of these microstrip blocks do, for example, anything through here gets a little confusing. If you just click this little help in the corner, okay, you can, you're able to find, let's go search, and to go branch line coupler. And 3D simulation, let's just write microstrip and microstrip line block. And then here we go, we've got all the blocks on the side, and we can go to branchline coupler. And now it's got all the parameters here that you can work with. So that's one easy way to figure out what all these values actually do. Okay, so please do go ahead and try stuff. You know, we've got radial stubs, we've got all different types of bends. Remember, if you do expect a bend to be in your final design, always account for it in the schematic tool, because your goal in the schematic tool is to do quick, very fast prototyping and optimization of full circuits that you then expect to transform into 3D. However, you don't want to do it straight away into 3D because you want to fine tune values, and you don't have, 6 years to do evolution strategy in 3D, which is, it doesn't seem viable without a supercomputer. Anyways, this was just a quick overview about microstrip blocks, how to account for discontinuities, and how to do wideband impedance matching. So thank you very much for watching.